In my previous videos, DHT11 sensor was programmed in C++ using ready-made libraries to display temperature and humidity measurements. In this video, DHT11 sensor is programmed in assembly to display temperature and humidity measurements on LED displays. DHT11 sensor is a digital sensor which is serially interfaced with a microcontroller using a one-wire bus. The microcontroller acts as the master while the sensor acts as the slave. The communication between the two devices is asynchronous, meaning that the microcontroller will request data from the slave, and the slave will then respond by sending the data to the microcontroller. To understand the asynchronous communication between the microcontroller and the sensor, we need to look at this timing diagram. The microcontroller will begin by requesting data from the sensor by sending a start signal, which is made of a low pulse and then a high pulse. And the sensor will then reply by sending the response signal, which is made of a low pulse and then a high pulse. Once the sensor sends the response signal, it then sends the 40-bit data serially to the microcontroller. And the microcontroller must be able to detect and store this 40-bit data. The sensor encodes the 40-bit data in high pulses, where for logic 0 the high pulse will have a pulse width of 26 microseconds, while for high pulse to represent logic 1, the pulse width would be 70 microseconds. Now let's look at how we can program the ATmega328 in assembly so that the controller sends the start signal and then receives the response signal. We assume that the sensor is connected to pin PB1 of port B. So first we need to set pin PB1 as output, and then we send a low pulse, and then we apply a delay of approximately 20 milliseconds, and then we apply a high pulse. Now the sensor will respond by sending the response signal, and the microcontroller needs to detect this response signal. So first we need to set pin PB1 as input, and then using this indefinite loop we are checking for the low pulse. Once the low pulse is detected, then we go to the next indefinite loop and check for the high pulse, and then afterwards we check for the low pulse. Once the microcontroller receives the response signal, it is ready to receive the data from the sensor. So let's see how it receives the first byte of data. The idea is the microcontroller should first detect a high pulse because it represents the ones and zeros of the data. Once it is detected the high pulse, then it will wait for 50 microseconds and then determine whether this high pulse represented a logic 0 or a logic 1. So for example, for this case, after 50 milliseconds, the logic is 0, while for this pulse here, after 50 milliseconds, the logic is 1. The microcontroller detects the high pulse by using this indefinite loop. Once the high pulse is detected, then a delay of 50 milliseconds is applied. And timer 0 is used here to apply the delay for its high accuracy. Once the high pulse is detected, we need to determine whether it is a logic 0 or a logic 1, and then save the logic in a register. And we need to repeat this 8 times to cover the 8 bits of received data. The next slide will demonstrate how we determine the bit value and how we store it in a register. As an example, let's say the sensor sends this byte of data to the microcontroller, and this represents the most significant bit, so this is shifted in first into the controller, and we need to determine whether this bit is a 1 or 0. We can do this by using this instruction here, skip if bit is set. So in this example we have a 1, so this instruction becomes true. We skip the jump, we go to the next instruction. Now we are using register R18 to store the received bits, and we are also using the carry flag. So the next instruction here is to set the carry flag. We set the carry flag, and then we use this instruction rotate through carry left. So the carry value will be shifted into the least significant bit of R18, and the rest of the R18 bits will be shifted to the left. Next we receive a logic 0, and this instruction becomes false, and we jump to label skip, and here we apply a logical shift left, which means a 0 will be shifted into the least significant bit of R18 and the rest of the bits will be shifted to the left, and we have this result. Repeating this code 8 times will ensure that the 8-bit receive value will now be stored in register R18. The 40-bit data sent by this sensor is made of 5 bytes. The first byte is the integer value of the humidity. The second byte is the decimal value of the humidity. Third byte is the integer value of temperature. The fourth byte is the decimal value of the temperature. And the last byte is the checksum. The checksum byte can be used to determine that the 4 received bytes are correct. And we can do this by adding the 4 byte values, and they should sum up to the checksum. In this video we'll not be looking into the checksum. This will be left for a future video, and in this video we'll be extracting only the integer part of the humidity and the integer part of the temperature and display it on byte registers of the 80 mega microcontroller. In this project the temperature and humidity measurements are displayed on LEDs connected to 2 ports. So we have the humidity byte is displayed on port D, and the temperature byte is displayed on port C. Now we only have access to 6 pins of port C, so we have only 6 LEDs connected to port C. And now for a quick demonstration. The humidity byte is displayed on port D, and the temperature is displayed on port C. A quick look at the assembly code. We set port C and D as output ports, and then we call the subroutine to apply a delay of 2 seconds in order for the DHT11 to get ready. After a delay of 2 seconds, we begin by sending the start pulse. First we send the low pulse, a delay of 20 milliseconds, and then we send the high pulse. Next the code receives the response signal. So first we receive the low pulse, and then we receive the high pulse, and then the low pulse of the response signal. Next we call the subroutine to read the first byte of the 40-bit data, and this is the integer part of the humidity. Inside subroutine DHT11 reading, first we set up a counter for receiving the 8 bits, and then we assign register R18 to store the data. First we need to clear this register, and then we use this indefinite loop to detect the high pulse, which is the data bit, and then we apply a delay of 50 microseconds by calling a function that uses timer 0 for the delay. This part of the code will detect and store the data bit, and this was explained in a previous slide. Next we wait for the low pulse, and then we decrement the counter, and then we go back and detect the next bit. And once all of the 8 bits have been stored in register R18, we return to the calling subroutine. Back inside the main subroutine, we store a copy of the received byte into register R19, and then we call the subroutine again, DHT11 reading, in order to get the second byte, and then we call the subroutine for the third time in order to get the third byte, which represents the integer part of the temperature. Then we output the temperature to port C, and we output the humidity to port D, and we go back and get another sensor reading. A quick look at the delay subroutines used in this code. This subroutine uses a nested loop to give us a 20 millisecond delay. And this subroutine uses another nested loop to give us a 2-second delay. And this subroutine uses timer 0 in CTC mode to give us a delay of 50 microseconds. Please refer to my previous videos for detailed explanation. In my next video, I will modify the assembly code to display temperature and humidity measurements on a MAX 7219 display. Thank you for watching.